Section 5 is on Graham's law and Dalton's law, so two more gas laws. Effusion. So we've mentioned this before. It's the movement of gas through a small opening in a pressurized container. And I've addressed this as well. Do all gases move at different rates? And the answer is yes. They don't move at the same velocity. They have the same kinetic energy. And the kinetic energy here should be, change this over here, is 1/2 mv squared. Okay, but they all have the same kinetic energy, but they have different masses, which means they are going to be moving at different velocities so that their kinetic energies are all the same. So if the temperature is the same, then the kinetic energy is the same. Therefore, gases at the same temperature must be moving at different rates if they have different masses, which they do. So the law that we're going to get from this is going to end up being Graham's law. Which gases move faster, which ones move slower? Thomas Graham determined an inverse relationship between effusion rates and molar mass. Graham's law is actually a proportion, not an equation, and that's what this little symbol right here means. It means proportional. The rate of effusion is proportional to 1 over the square root of the molar mass. Okay? And then as far as like how we apply this, well, there's actually is a way to get an equation out of this. And essentially, by looking at this right here, the gas that's going to weigh more, right, if I have a larger denominator, it's going to move slower, right? 1 divided by a bigger number is going to give you a smaller number, versus 1 divided by a small number, right? That'll give you a larger rate of effusion. So the lighter gases, and this is the relationship you want to remember, the lighter it is in terms of its molecular weight, okay, is faster. The lighter it is, the faster it's going to go. So between helium or xenon, right, helium is going to move faster. It's much, much lighter. Okay, so as an equation, it'll look like diffusion, the movement of one material through another. It looks like this, and all this is, it's really just rearranging the kinetic energy equation. Since we're saying gases in the same temperature have to be, right, both equal to the same kinetic energy, all Graham did was just rearrange this, and it looks like this. So basically, he had 1/2 mv squared is equal to 1/2 mv squared of the second gas. Well, the 1/2s would cancel out here, and then you have, right, the velocities and the masses, and they rearrange to look like this. Rate of gas A, which he's using as velocity, over rate of gas B is equal to the square root of the molar mass of B over the molar mass of A. Okay, the most common mistake with this, as you can probably guess, is making sure that we put the right substance in the right spot. All right, if we notice here, it's rate A over B is equal to the square root of the molar mass of B over A. Okay, so they're flipped there. So don't make that mistake when you are using this equation. But what this does is it gives us relative rates. Now, maybe the question would give us an exact number, but what it does is it tells us relative rates. How much faster is one gas moving compared to another? Okay, it's not going to necessarily give you an exact number unless the problem gives you an exact rate. Okay, this is just going to give us a relationship of how much faster A is than B or how much faster B is than A. That's what this does. So let's try this problem here. Ammonia has a molar mass of 17.04 grams per mole. Hydrogen chloride has a molar mass of 36.46 grams per mole. What is the ratio of their diffusion rates? Okay, so my equation is the rate of A over the rate of B is equal to the square root of the molar mass of B over the molar mass of A. Okay, and what we can do here is let's just go ahead and assume that since we want B to be probably the larger number, that'll make it a little bit easier to do here. And let's just assign which gas is which. So we'll say hydrogen chloride is B and ammonia is A. So that means the rate of ammonia compared to the rate of HCl as hydrogen chloride is equal to the square root of 36.46 grams per mole over 17.04 grams per mole. If you notice here, all the units cancel, so the number I'm going to get actually has no units. Okay, so if I plug that in, 36.46 divided by 17.04, and take the square root of that, and we will use four significant figures, 1.463. There's no units associated with this. What this means is that ammonia, okay, moves 1.463 times faster than HCl. If you wanted to, you could write this over 1. Oops, Apple Pencil messed up there. You could write it over 1, and all that shows you is that HCl's rate is 1 relative to ammonia's, which would be 1.463. Okay, so it's just telling you how much faster one gas is moving than the other. Okay, Dalton's law. Dalton is going to determine that each gas in a mixture exerts pressure independently of the other gases present. Okay, so it doesn't matter how many different gases you have in there, that they are all going to add to the total pressure of a container. So let's say you have a container with multiple gases. Those pressures from each individual gas add up to the total pressure. Okay, so Dalton's law of partial pressures, the total pressure of a mixture of gases is equal to the sum of the pressure of all the gases in the mixture. Right, so this is like you've got a container here with, several things, CO2, O2, helium, whatever, and each one of those gases exerts its own pressure on the walls of the container, and the container experiences the pressure of all three added up. Okay, so it doesn't experience some lesser amount or greater amount, it's just all three added up. Okay, so what this looks like is the total pressure is the pressure of gas 1 plus the pressure of gas 2 plus the pressure of however many gases out to, right, some number in. So if you've got 15 gases there, you have 15 pressures to add up. So that's what that looks like. So it means you may have to find pressures of individual gases. So as a sample problem here, a mixture of O2, CO2, and N2 has a total pressure of 0.97 atmospheres. What is the partial pressure of O2 if the partial pressure of CO2 is 0.70 and the partial pressure of N2 is 0.12. So we have total pressure is the sum of all three of them. Pressure of O2 plus the pressure of CO2 plus the pressure of N2. And if you had more gases, you'd add more. If you only had two, you only have two. Well, we have 0.97 atmospheres on the left side. We don't know the pressure of O2. We know the pressure of CO2 is 0.70 atmospheres. And we know the pressure of N2 is 0.12 atmospheres. Okay, so here we're just going to take 0.97 minus 0.7 minus 0.12. Okay, and we wind up with the pressure of oxygen is 0.15 atmospheres. Now, certainly this is one of the easiest versions of this equation because I gave you numbers in atmospheres already. The homework questions that involve Dalton's law aren't going to just give you those numbers directly. They may have you solve using the ideal gas law. Dalton's law is often partnered with Puvnerd, PV equals nRT. Okay, so when you see Dalton's law, you're very often going to have to use this if they don't give you pressures directly like I just did right here. Okay, so doing the first problem off of the 8.5 worksheet, this is going to be a Dalton's law type of problem. Now, on the previous slide, I just told you you can expect the ones on the homework to be a little bit more complicated than just adding up pressures. So what we need to do here, let's read the question. After 0.600 liters of argon at 1.20 atmospheres and 227 degrees Celsius is mixed with 0.200 liters of oxygen at 501 torr and 127 degrees Celsius in a 400 milliliter flask at 27 degrees Celsius, what is the pressure in the flask? So a lot of stuff there to try to digest. They give you situation number 1 and tell you this is for argon, right? That's what this is for, okay? And they give you all the details of it except for the number of moles. And they give you a second set of conditions and say this is for oxygen, right? And they give you everything except for some number of moles. And then they say if we add them together, what's the pressure in the flask? So what we need to do here is figure out from this first, how many moles of argon do I have? How many moles of oxygen do I have? When I add them together, my number of moles in situation number 3 is moles of argon plus moles of oxygen, right? So that's what that is. And it tells us our volume was 400 milliliters or 0.400 liters. And it gave us a temperature and it wants to know the pressure. So the first thing I have to do is take these two situations and solve for the number of moles, add those together, and then we can figure out what the pressure is. So from situation number 1 here, right, N is equal to PV over RT. Okay, and if you plugged all those numbers in, 1.20 atmospheres times a volume of 0.600 liters, all that divided by 0.0821 liter atmospheres over moles times Kelvin times 500 for Kelvin. Okay, the number of moles there for the first one is, let's see, this is 0.0175. Okay, we'll do the same thing for situation number 2. Find the number of moles. Okay, so in this situation, my pressure is 0.659 atmospheres. And yes, it has to be an atmosphere, so you have to convert that torr over. Volume this time is 0.200 liters divided by R, 0.0821 times K, which is 400. Okay, so typing that in, this gives us 0.00401 moles. Alright, let's see if I can shrink this down now. Give myself some more room. So solving now for situation number 3, my number of moles are the 2 moles added together, 0.0175 plus 0.00401, and we'll round this to the, let's see here, 10,000ths place, so this is 0.0215 moles of gas, right? That is moles of argon and oxygen added together. So now I need to solve for pressure in situation number 3, so that's nRT over V. So I have 0.0215 moles times R, which is 0.0821 liters times atmospheres over moles times Kelvin, times T in the third situation is 300, divided by the volume, which was 0.400 liters, and let's see what our new pressure is. And this is 1.32 atmospheres. So just checking, is that a reasonable number? Yeah, I mean, it's not an outrageous pressure. I started with 1.2 atmospheres up here and 0.659 atmospheres on that side. It didn't have any crazy temperature changes. So this is just ballpark eyeballing. It's probably got to be about right. So there you go.